Sleep occupies roughly 1/3 of human life, yet for centuries it was considered a passive, dormant state. Modern neuroscience reveals the opposite. The sleeping brain is one of the most active and precisely orchestrated biological systems we know of. Over the next several minutes, we will examine exactly what the brain does during each stage of sleep and why that activity is essential to health, memory, and cognition. A typical night of sleep consists of 4 to 6 complete cycles, each lasting roughly 90 minutes. Across those cycles, approximately 25% of total sleep time is spent in REM, the phase most associated with dreaming and cognitive restoration. These numbers are not fixed. They shift across the lifespan and in response to sleep debt. Far from shutting down, the sleeping brain engages in complex, tightly regulated activity. Neurons across the cortex fire in synchronized bursts. Metabolic rates remain elevated, and discrete biological programs execute, each tied to a specific sleep phase. The key distinction from wakefulness is not activity level, but activity pattern. Sleep is divided into 4 distinct stages, 3 non-REM stages and 1 REM stage. Each is defined by a unique electroencephalogram signature and a specific set of physiological events. A complete sleep cycle moves through N1, N2, N3, and then REM before returning to the beginning, with a proportion of deep sleep declining and REM lengthening as the night progresses. N2 constitutes the single largest portion of sleep, approximately 45%. N3, deep sleep, and REM each account for roughly 25% of the night, while N1 is a brief transitional phase at around 5%. These proportions shift with age. Children spend significantly more time in N3, while REM consolidation peaks in young adulthood. During N3, also called slow-wave sleep, the cortex produces large, sweeping delta waves as thousands of neurons fire in near-perfect synchrony. This is the deepest and most physically restorative stage of sleep. The body repairs muscle and tissue, the immune system consolidates its defenses, and the brain executes synaptic homeostasis, selectively strengthening key connections while pruning weaker ones. REM sleep presents a neurological paradox. The brain generates vivid, immersive experiences while the body is rendered nearly motionless. The prefrontal cortex, responsible for rational oversight and critical evaluation, is suppressed during REM, which explains why dreams feel compelling and uncritical, even as the sensory cortices run at full intensity. This suppression appears to be a feature, not a bug. It allows the brain to explore emotional memory without the constraints of waking logic. NREM and REM serve complementary but distinct functions. NREM prioritizes physical restoration and declarative memory consolidation, the encoding of facts and events. REM focuses on emotional processing and procedural learning, skills and emotional associations. Both phases are essential. Chronic loss of either produces measurable cognitive and physiological deficits, and they cannot substitute for each other. One of sleep's most critical roles is converting short-term memories into durable, long-term knowledge. The hippocampus, which temporarily stores new information acquired during the day, coordinates with the neocortex during sleep to offload and consolidate those memories. This transfer requires both NREM and REM cycles. Studies show that interrupting either phase selectively impairs different categories of memory. A network of fluid channels surrounding the brain's blood vessels, the glymphatic system, becomes dramatically more active during sleep. Cerebrospinal fluid floods through these enlarged channels, washing out toxic metabolic byproducts, including amyloid beta, the protein implicated in Alzheimer's disease. This cleansing process operates almost exclusively during sleep and is most active during N3 slow-wave sleep. Sleep orchestrates a precisely timed hormonal cascade. Growth hormone surges during the first deep sleep cycle to initiate physical repair and tissue regeneration. Melatonin, produced by the pineal gland, maintains sleep pressure across the night. Cortisol follows an inverse arc, lowest in the first half of the night and rising steeply toward dawn, preparing the body and brain for the demands of waking life. The consequences of sleep deprivation are measurable within a single night. After 24 hours without sleep, cognitive performance degrades to a level comparable to legal intoxication. The brain's capacity to form new memories drops by 40%. Meanwhile, metabolic waste clearance in the glymphatic system nearly halts, and amyloid beta accumulates at significantly elevated rates, a pattern associated with long-term neurodegenerative risk. Sleep is governed by two independent but interacting biological systems. The circadian clock, anchored in the suprachiasmatic nucleus, generates a 24-hour oscillation that determines the optimal window for sleep. Separately, adenosine accumulates in the brain throughout the day, creating mounting pressure to sleep. Caffeine works by blocking adenosine receptors, suppressing the signal of sleep pressure without actually reducing it. Every night, the sleeping brain executes a coordinated sequence of critical operations. It cycles through stages, consolidates the day's learning, repairs the body, removes accumulated toxins, and recalibrates its hormonal systems. Each function is time-locked to specific sleep stages, which is why both duration and continuity of sleep matter. Fragmented or shortened sleep does not simply reduce these processes, it disrupts their sequencing entirely. The brain does not shut down during sleep. It shifts into a different and irreplaceable mode of operation, one that is essential to cognition, health, and longevity. Prioritizing consistent, full-duration sleep is among the highest leverage actions available for brain health and long-term performance. Sleep is not time lost to unconsciousness, it is time invested in the brain's capacity to function.